Okay, happy Thursday. How's everyone doing? Hopefully better than I've been the past couple of days. I still have like a thing in my throat. Hopefully that doesn't throw us off too much today. We will. You're gonna have to struggle through my voice. So we'll see how things go. Um, so you may have noticed I moved back the mini exam from Tuesday just because I was feeling terrible. Um, so we're going to sort of wrap that in with the mini exam on Tuesday next week. I'll send out more information about how that will exactly go. I've also pushed back the homework, so I'm going to post it, and we'll talk through like due dates and all of that. But basically, it's going to be wrapped into the next homework. So it'll be a little bit longer than normal, but nothing too unwieldy. What we're doing today is finishing up what we did at the end of class a week ago. It's been a week since we've seen each other. It's nice seeing everyone. We spent some time talking about time series, and we didn't quite get through everything I wanted to discuss with time series. So we're going to sort of conclude what we did in class on Thursday last week, and then we're going to do some fun stuff. I spent a lot of time working with maps, and so I wanted to cover just sort of in one class period, less than one class period, just some of the ways we think about geographic data. I know some of you, I've talked to some of you about working with maps and geographic data. I know some of you will be interested in using this type of data for what you're doing in this class, your project. So I'm going to show you some examples. I used maps in my dissertation, which is fun. I can show you more about that if you're interested. And we're going to talk about like a project I worked on, and a big project in the field of economics using geographic data and historical data. That's where we're going. We're also going to talk about an example using Pittsburgh-specific data. So we're going to walk through how to actually make some maps, construct some distances, and then plot some, some relevant information to geography in Pittsburgh. So that's where we're going today. Before we get in, are there any questions? Anything I missed? Yes.
I can't access the slides.
So let's see. This should be on 2.2, or I'm sorry, 2.3. If you refresh the page, I just posted it like 10 minutes ago. So you should have access to it here. Oh, hold on a second. This is what my website looks like behind the scenes. And then I just post it to GitHub. So that'll be up there in a couple minutes. You'll just have to refresh the page eventually, but it should be ready in just a couple. Okay, other questions? Thanks, Garrett. What else? Also, I've noticed the live streams of this class, the audio is really bad. So I'm working on figuring out why that is, in case you need to access it later. So yeah, take a look at that if you need to. So yeah, I'll send out more information about the logistics for the pushback assessments, just because I embody a mortal frame and I sometimes get sick. Happens about once a year, usually in February. Okay, so you'll remember what we walked through last time. We talked about box plots. You've all seen box plots, so this was really a refresher. We talked about coffee importing countries and their coffee consumption. And we asked the question, does this data confirm the world is drinking more coffee? And so we just looked at, the distribution of coffee consumption by country in each one of these years, and used box plots to be able to tell us different things about the distributions. So it was a big question. It's hard to answer that simply looking at these box plots. So we asked a smaller question, consuming less than 5 per capita, and we used the median to allow us to understand how many countries are consuming less than 5 kilograms, whether the median was consuming less than 5 kilograms. And then, so you remember we just walked through a bunch of questions using the box plots to sort of make comparisons. And this was, we spent a lot of time sort of talking about using box plots to make comparisons like this. And then we also talked about multi-period box plots. So we used this coffee per capita data set, which was in our week 5 folder. So you'll remember we had a bunch of countries and we had a bunch of years, which represented, coffee consumption per capita in each one of these years by each one of these countries. So sort of this is a panel data. We have a sequence for each country. So our unit of observation is tracked through time. And so what we did is we talked about, 2 particular years, and we used our scatter plot to be able to compare changes. So a relatively simple application of a scatter plot. But this is a fundamentally different way of using a scatter plot than what we had done before. In the past, we made comparisons between like GDP and production by country in a particular year, which allowed us to examine a relationship between 2 different variables at one point in time. And what we did here was use 2 different points in time to measure changes, which is a really powerful use of a scatter plot. So this was, I think, one of the more powerful ways of using scatter plots. And using a horizontal line, a 45-degree line like this, allows us to make visual comparisons through time much more easily. So the countries we saw with decreased coffee consumption would be below this 45-degree line. And then we can translate this back into a log scale and then use colors to visually represent countries with an increased coffee consumption and a decreased coffee consumption. And I think we didn't actually do this in a notebook, correct? Does anyone remember doing this in a notebook? Yes? Oh, we did do it. Okay. So if you don't remember walking through, just take a look at the notebook. It's a great movie. You can find it right here. So you can just click on this. It'll open it up for you. Unfortunately, there's no Ryan Gosling in this one. But you can definitely make some nice plots. So you'll remember we walked through. We opened the data set, loaded it, confirmed it looked correct, and then created a box plot for one given year, our base year. We created the multiple box plots, and then created a scatter plot with 2 years. So there's, you can do a lot with these things. None of the skills involved in creating the scatter plot are brand new. We have a data filter, so we filter for all of the countries above and below some ratio, and then we scatter one, and we color it green, and then we scatter the other, color it red, and then we just apply some labels. So everything we've done here is, a sort of a combination of the tools we've done before. And then here we're just applying a log. So we're just transforming our linear variables into log variables simply by applying mp.log base 10. or I guess in this case, base 2. It doesn't matter so much which base we use. Okay. So this is what we did last time. I believe we also talked through some of the CPI measures. So I just want to refresh your memory of what we've done. So, we talked about a big question, which was like, how do we pick prices next month? And again, I've still not updated my slides. I'm still stuck in the past. You're supposed to laugh at my self-deprecating humor, even when my voice is terrible. So we're trying to pick prices next month, and we have a distribution of historic prices during this time. This is really not very helpful. So one way we organize time series data is with two axes. So we have a vertical axis, which is price, and then horizontal axis, which is time. Excuse me. But, when we plot these things, because there's a sequence, we actually want to connect the points together. So we connected them together, and then we backed way out. So we looked at a much longer time series. We talked about, ways of visually showing increases or decreases in price. You can color these gray to represent copy decreases. You could also color each one of these years green or red if you wanted to show increase or decrease. There are lots of ways of doing this, but sort of background color like this is one way we use to talk about trends. And then we backed way out, and we said we could go all the way back to 1974, roughly, and think about copy prices. But if you know anything about economics, right, prices, so like $1 doesn't carry the same value at two different points in time. And so when we're thinking about changes in prices, one thing we do, standard practice in economics, is try to normalize by some measure of inflation. So one thing we can do before we do any transformations is, talk about, $1 in 1974 and how much it would be worth today. So amazingly, I don't know if you realize this, $1 in 1974 is worth like roughly $8 today. Like it's gone up like roughly 8 times. Kind of wild. That generally blows my mind. Like my parents were, in high school around this time. So like money has become a quarter of what it was worth when my parents were in high school. Amazing. So, as economists, we like not just to think about like the raw numbers, but also the ones that are kind of normalized. So I don't do macroeconomics. It's not really a thing I do. But if we were thinking about prices over this period, we would need to adjust for inflation. And so what we can do is just create a normalized variable. So what I did most of the work for you, but we can load this data set of copy prices and CPI into this data set, into this notebook. And I think this is not what we did in class, correct? Okay, if it isn't looking familiar, I'm going to spend just a second talking this through. So we just load the data set, we make sure it looks familiar. We have, our date, we have our nominal price. So this is like the actual number. We have the year, and then we have the dollar value today. So how much a dollar today would be worth in whatever year we're looking at. So in this case, a dollar today in 1973 would be worth 14 cents. Amazing. Crazy. That's like less than a quarter. So then we also have the CPI measure. So I did the hard work. I translated CPI into dollar today, and then we can just plot what this looks like. So it's like a very steady increase. And so all we have to do to convert nominal price into real price is with this inflation conversion. Bless me. So we just divide the base dollar by the nominal price, and then we plot this. So that's what I've done in the slides. This allows us to make adjustments for inflation. Okay, any questions here? So has price gone down? Certainly. I think this makes it pretty clear. Price of coffee is way lower than it was in the 70s and even in the 80s. It's maybe dropped by half of the price it was in the 80s. But roughly since 1990, it's been about the same price, with a couple of spikes. Okay. So this is one thing we did. We examined coffee prices and adjusted them for inflation. This is one of those things you as a economic data analyst will have to work with pretty frequently. Transforming data, particularly prices, from nominal into real. It's a pretty standard conversion. It's not a thing I do that often, but it's something that economists do a lot of. Okay. So one thing we often encounter is not just sort of, variation through time, but sometimes certain things change based on season. So I don't know about you, I like to eat blueberries. It's weirdly one of my favorite foods. So I go to my local Aldi and I buy blueberries. And depending on the season, they can be better or worse. And depending on the season, they're going to have different prices. It's sort of less true today than it was like 50 years ago, but we have this seasonality with certain things. And so one thing we might care about is the price of coffee by season. So where before we were considering box plots by year, we can also think about not just year variation, but also is there something consistent going on in the variation by season? So here I have month, this is January, and we have our standard box plot. But we can also plot out prices across years. Sorry, across months. So we have all of our coffee price data broken out by a single month. So no matter what the year is, if it's in January, it falls in the January box plot. Okay, so we can go through and ask some questions. So can you spare me my voice for a second? Can you answer this question? In which month was the record highest price set? Corin.
April.
And we're looking at April. Corin's looking at this high point. We're saying, which maximum occurred in which month. And so April had the highest maximum. And then which season are prices most spread out? I'm sorry. Ben.
Spring.
It's because I'm getting over a cold. I'm going to blame it on so spring. So we're going to look at these 3 months, March, April, May, we have the largest spread. Basically, the minimums are all the same. We're just going to look at the ones with highest maximums. Yeah, thank you, Ben. Okay, so roughly spring. Can someone tell me the trend in the median price? Yeah, Joey.
It's all roughly the same for the median amount.
So from this, it looks like it's roughly the same. We've talked about like problems of scale. right? Like it's hard to see variation when we're zoomed way out. One of the problems with box plots is we have, 4 different scales going on. We have the minimum, or I guess 5. Minimum, the 3 interquartiles, and then the maximum. So one thing we can do is instead of plotting box plots, we could plot by month each one of the quartiles, min through max, like this. So this is another way of seeing the data. Instead of looking at box plots, we'll just use the 5 quartiles. And this gives us maybe a slightly different picture. If we're interested in the median, we can just get rid of all of the other quartiles and just look at the median and plot that as a time series across months. And I don't know. I don't know what's going on with this figure. Someone want to what do you see when you see this? The median seems to move around a lot in ways that are not so consistent, I would say. This looks like mush to me. Not a lot of clear trends across season. Okay, so this is, I think sometimes your data will be amenable to this type of visualization tool. So I like to include it here just to show that, we can go from a box plot, a series of box plots like this, and display the same type of information just with maybe a little less clutter in this way. Okay, so the last thing we're going to do with time series is talk about multiple relationships through time. So one thing, so we have this price of coffee and price of oil. Coffee is a nice thing. Oil is breaking our planet. What do you see with this figure? Part of the skill set we're trying to develop is not just can you read a figure, but can you tell me maybe how to interpret a figure, and then also how to make a figure more interpretable. Yeah, Corin.
You can't really interpret much because the scale of the prices is just so different.
So problem with scale. We have, the price of oil. If we go to our data set, the price of oil is it's like hundreds of dollars. So, on the scale of hundreds of dollars. Where the price of coffee per pound, the green beans before they're roasted, is, on the order of single dollars. So these scales are not that consistent. So it makes it really hard to see what's going on. So someone remind me what we do in this case? Yeah. So you could potentially look at the log of the 2 axes, and that may fix the problem in some cases. There's another thing we did. It's Ben, right? So one approach that we typically take to make comparisons between large and small values is to take a log. But in this case, I think there's actually a maybe more useful approach. But log is definitely something we can do. What's maybe another way of visualizing the different scales? We've done it once before. What if we use 2 axes? So each of the 2 lines has their own scale. So on the right-hand side, we have the price of oil, and then on the left-hand side, we have the price of coffee. Is this easier to read? Maybe a little bit. There's still a lot of clutter. I made this figure a couple months ago. I'd probably take out the grid lines behind the scenes. It kind of adds some clutter. But if you're trying to interpret what the potential relationship is between coffee prices and oil prices, someone tell me what this generally looks like. Yeah, Drew.
There's like a sharp increase in like kind of time period.
Yes. Yeah, so they're like generally kind of moving in the same direction. Drew's pointing out the sharp increases in one being around the same time as a sharp increase in the other. And you can sort of generally see a sharp decrease leading, happening around the same time as a sharp decrease in the other. So it looks like the two lines are generally moving in the same directions. Any other observations here? So this is a pretty good figure. I mean, it's not a great figure, but like in terms of understanding what's going on with the data, this is one way of getting at it. We can also use one of our older tools to identify the points where they didn't move in the same direction. Sometimes we like to show confirming evidence, but as a social scientist or doing anything with a scientific method, you also want to try to investigate conditions where your hypothesis is wrong. You're looking for disconfirming evidence most of the time. So one thing we could do is identify the regions where the two prices are moving in the opposite directions from each other. So we can just identify those in gray. This is our main question potentially. And one thing we might do is instead of plotting these with a line graph where we have a horizontal axis representing time, maybe we don't care so much about time. Maybe all we care about is the position of these two prices at the same time. So what I've done here is created a scatter plot. So on the horizontal axis, I have coffee price per pound, and then on the vertical axis, I have oil prices in cubic meters. So this is one of those places where we don't have to worry so much about the scales. I mean, we do. We're like building the scales into the axes. But because we have two separate axes, we don't have to set up anything fancy with two scales, right? Because they're on different axes. And someone tell me, does this look like a positive or a negative or an unclear trend? Y'all are, okay. Yeah, I was going to say, y'all are doing my throat dirty by not answering my questions. Thanks, Garrett. So Garrett's saying positive trend, we have a positive relationship between these two variables. And we can say this because we use a scatter plot. So these are multiple points with 2 dimensions of data, and we just plot these on a scatter plot. Okay, any questions here? What about this last question? Someone interpret it for me. I'm going to give my throat a second to pause. I'm going to look for a yes or a no. How many of you say yes? Hands up. How many of you say no? Okay. We are going to build models of causality, like simple models of causality, when we start talking about multivariate regression. We need to understand how causation may not give us, how correlation may not give us causation. We're going to build really clear models of why these two may not be causally related to each other. The answer here is no. The price of oil doesn't necessarily determine the price of coffee. Although you can build models, like explanations for why it may be true. This is not enough information to be able to conclude that. We know they're correlated, or they're related in some way, but we don't know if they're causally related, simply from a graph like this. This is one of the most common mistakes people make, is to conclude that there's a causal relationship from this data simply because we can make the explanation for why it might be true. Oil going up may lead to higher transport costs and operating costs to manufacture and distribute coffee, which then may lead to higher prices of coffee. But this picture alone doesn't conclude that that's what's going on. It may be general distribution disruptions that may be causing both the higher price of coffee and the higher price of oil. So from this information, we don't have enough to conclude this. Okay, any questions here? All right, so this is the end of 2.2. We're going to spend the rest of class today talking about geographic data. This is near and dear to my heart. I've spent just so many years thinking about geographic data. How many of you have taken a GIS, Geographic Information Systems course? No one. Okay. I don't know for sure that Pitt offers one. I expect that it would. I took a GIS class in undergrad, and it was one of my favorites. And now I use geographic information in a lot of what I do. So we're going to talk through some examples of geographic information in economics literature and just try to classify geographic information and walk through one example that we're going to construct together in a notebook. Okay, so this is our example. How many of you think you might use geographic data in your final project, like spatial relationships? Okay, a lot of people potentially. If you're interested in spatial relationships, so like how close things matter more than further things, then this type of analysis is pretty powerful. Okay, so we're going to use census maps that we're going to download together, and OpenStreetMaps, which is a great way to access maps just through Python. Okay, so our main question is going to be, are restaurants, are there fewer restaurants in areas that are further away from downtown? So if you go downtown, you see like tons of restaurants, they're every corner, lots of places to eat. Oakland, similar, lots of places to eat. Are zip codes, so areas in Pittsburgh, that are further away from downtown, do they tend to have fewer restaurants available? And so what we're going to do is collect data on the locations of restaurants. It's not going to be every restaurant in Pittsburgh, but it's going to be some. And then we're also going to look at zip codes, and then we're going to construct a scatter plot to look at distance from downtown and number of restaurants. And we're going to do this from scratch. It's going to be pretty fun. Okay, so before we get started, I just want to sort of classify some types of geographic data. So typically, we have geographic data organized on 3 axes. You can sort of think about time as maybe a 4th one, but we don't often do more than 3 dimensions of geographic data. And typically, we only use 2. So we have latitude and longitude. So latitude is north-south, longitude is horizontal, and then altitude is just sort of your z direction, so like coming off the plane. We typically only look at latitude and longitude, which is what we're going to do today. But sometimes we consider altitude. Sometimes when you're like looking at a large enough geography, you have to account for the curvature of the Earth. But most of the applications you'll deal with don't have that problem. But I had to deal with this when measuring distances, which you'll see later. Okay, so we typically only use the 2 dimensions of a plane, latitude and longitude. And then we often combine location data with other variables like population, which I'll show you in a second. So we have sort of 2 main types of geographic data. We have points and we have shapes. And we're excuse me, my mortal frame is malfunctioning. So we're going to work with both of these today. Um, Points are less common to observe. We're going to work with them today. They're more powerful in a lot of ways. But sort of most of the time when you get data, it's going to be in groups. So, data by zip code or data by county, for example. This is the most common. Maps, are typically on 2 dimensions. We talked about the possibility of a 3rd dimension, but typically what we do is 2 dimensions. And just like a scatter plot, like this is the same software as what we use to make scatter plots. We just have 2 dimensions, these numbers representing latitude and longitude, and we're just going to plot a shape on a 2-dimensional graph, where on the vertical axis our y variable is latitude, and our horizontal variable is longitude. So if we hop over to the Colab notebook, we have our imports. So we'll just import these things. We're actually not going to interact with Google Drive today, so I don't have that loaded here. The one thing we have to do is install this package, OpenStreetMaps. So you just have to run this. This just installs it in your notebook, and then you can just hide this thing. So we'll hide that. Okay, and then we're just going to import a bunch of these things. All right, so the first thing we're going to do is just load up some restaurant data using OpenStreetMaps. And then we're just going to create a Pittsburgh boundary using OpenStreetMaps. So this is just, we're going to call OpenStreetMaps Pittsburgh, USA, and call it the Pittsburgh boundary. And then we're just going to plot it. So all we're doing, it's exactly the same approach as when we plot any variable, except here it's what we call a shape file, which is a piece of data that gives us sort of an area. It's like a shape on the 2-dimensional plane. And then all we're doing is setting the boundaries. Okay, so this is what I did here. I want to tell you, when I was constructing this example, I wrote basically none of this code from scratch. I talked to an AI, basically, talked through what I wanted to do in the example, and then it gave me the code. There's going to be some more complicated things we do later, and I want to confirm with you, I don't expect you to know how to do these things from scratch. Some of the tools may look familiar. Some of them will look a little more complicated. Like, how do you write all this? Frankly, I would not be able to do this without the help of AI or Google search. This is not something you need to know that we could do. So I just want to sort of mention that at the top. So anyway, we get a nice little plot of Pittsburgh, and this should look familiar. If you've been in Pittsburgh for any length of time, this shape should feel like home. At least it does for me. So we can also plot out Pittsburgh zip codes. So from the Census Bureau, we can download different geographies. So this is what, we have our full map here, but sometimes we like to think about, breaks or sub areas. And so what we can do is go over to our notebook, and what we're going to do is actually we're going to load a data set just directly from the Census Bureau. So we have the zip URL, and then we're just going to read that file from just directly into Python. GPD is the nickname we give to GeoPandas. So it's the panel data set that package we've been working with, but it's the geographic data version of pandas. It's what we call GeoPandas, which sounds like a great name for a movie. No one? Okay. Guess none of you are making it in Hollywood, like I will one day. Obvious joke. I can barely get a YouTube live stream to work. Okay, so what we're doing is loading a data set from the Census Bureau, census.gov, for a file. And it's going to give us a data set with zip codes. So if you look at this, one thing we could do is just look at what it looks like, zipcodes.head. So it operates exactly the same way as every other kind of data set we've worked with. And when this prints out, you can see we have different geographic codes here, but you can see the latitude and longitude here, and then not a lot of information that's given. So you need to know something about what each one of these variables is doing. This looks like land area, and then water area. So this contains no water. And then these are zip codes. So each one of these zip codes gives us a particular area. And then so all we want to do, we don't actually want every zip code in the US, we just want the ones that are in Pittsburgh. So what I'm going to do is actually convert the Pittsburgh boundary into the same sort of coordinate system. This is just one of those things we have to do with geographic data. We're going to change coordinate system, but then we're going to get the zip codes that overlap with the Pittsburgh shapefile. So we're just going to get the overlap area, the intersection. So when we run this, it'll give us all of the Pittsburgh zip codes, and then we'll just plot those things. Which gives us this. I've added a bunch of code here to make it look pretty, but if you wanted to just do the basics, you'd get the axes, which would be fine. But I like to clear those out when I make a figure, so I've included this code below. Any questions here? So remember what we did. We found the shape for Pittsburgh. We found all of the zip codes in the US, and then we selected the zip codes that sit on top of Pittsburgh. And that gives us the Pittsburgh zip codes. Okay, so nice. And then one thing we can do actually with maps like this is change the colors. So if you want to show like population by zip code, one thing you could do is just color each one of these areas based on its population. And so what I've done here is do just that. So these different areas represent different population counts. And you can see the population count on the color gradient on the side. So this is one way you often see data visualized geographically, is using color gradients. I live in this one, which is lower density. And we are currently in Oakland, which is this one. Okay, and then you can also create interactive maps. So this is an interactive slide, so you should be able to access this from the link I posted for the slides. But you can actually go through and hover over each one of these areas and get the population. These aren't like current best estimates for the areas, but they're pretty close. And then you can also like zoom in. So you can sort of take a look at any one of these little areas. And you can see the base map too. So you can see the streets and all of that. Okay, any questions here? So feel free to play around with this. This is in the slides that are on the part 2 page. These are all the zip codes. We also would like to, our main question is about restaurants. So we can create a subset of all the restaurants in Pittsburgh and plot them on our zip code map. So what I'm going to do in the notebook, is, remember we created a restaurants data set above and looked like this. We imported it from OpenStreetMap, and then we got all of the places in Pittsburgh that are, their amenity is a restaurant. And then we just created the data set. So, anyone been to Tram's Kitchen? I have. It's like better than average, but not my favorite. So you can go through and look at all the different restaurants, but we can also just plot them on our zip code map. So here I plotted all of the zip codes like before, but then on top of it, I've laid out all the restaurants as geographic points. So you can run this, and it'll give us the map of Pittsburgh with some restaurants. There are going to be obvious ones that are left out. My favorite restaurants are not on this list, but we do have a lot of restaurants included. Okay, so this is this is one way of displaying data. We have sort of two types of data. We have our areas, our zip codes, and then we also have the points that sit on top of them. And if you're interested, I've included an interactive map here too. So you can go around. So right now we're in this building, and then you can look at some of the. Anyone like Viva Los Tacos? No.
Got worse. Birria tacos used to be really good.
Okay. Wait, what did you say?
The birria tacos used to be
Ah, okay. But they got worse.
Yeah, it's not like all tacos. Now it's like burgers.
Shoot, yeah, that's weird. There's definitely way better tacos in Pittsburgh than here.
Why would you sell burgers?
Let's see. So fuel and fuddle. Is that gone?
Yeah, it's not existent.
So this is out of date, apparently. I remember being on Reddit, reading people talk about the new place. What's it called? Like it's like a stew place.
It was stew, now it's like a Latino place or something.
Okay, interesting.
Two restaurants out there.
Shoot, yeah. Altoons. People love Altoons. Do you all love Altoons?
Love is a strong word.
Love?
I tolerate all too.
Tolerate, okay. So
Cheap pizza.
tolerate good pizza for the price. Okay, so you can go around. My favorite restaurant is not on this list, People's, but it's pretty good. At least includes a lot of data points. So feel free to play around with that. You can investigate little parts of Pittsburgh, and Google Maps is maybe a better way to do it. But we've created a map here, and I've included. Actually, I don't think I've included it in the notebook, but you can ask Gemini how to do it. It's pretty straightforward. Okay, any questions here? Okay, so this is information about zip codes and information about how they're laid out in space, and information about restaurants that's overlaid on top of zip codes. But remember our question. We're trying to think about restaurants by zip code and how that relates to distance from downtown. So the data is not in the right form. And so like we've done before, we have to apply data transformations to this data to allow us to answer the question that we're after. Points are very nice, but they don't allow us to directly answer many questions on their own. So we have to do some sort of transformation to the data points to make them better. Some of these transformations that we're going to use today are distances between points and groups by area. So we're going to count the number of restaurants that sit on top of each one of the zip codes. And then we're going to construct a distance between each one of the zip codes to the downtown zip code. This is going to allow us to answer our question. And then we can also relate points to other variables like population. So I want to talk through two examples in the economics literature, some like famous papers that we talk about in economics. This is a really powerful one. The question at hand was, did the historical trade of enslaved people impact the modern development in Africa? So obviously a really important question, one we would love to know the answer to. The short answer is yes. But what this paper did is they used historical data, and then they measured distances between like historical boundaries in Africa to major ports of the time, and then used that as a way of trying to understand the disruption from enslavement. And what they found is, unsurprisingly, we have a pretty big disruption from the slave trade, even on GDP today. Some of these things are coming from weakened institutions and the disruption just culturally at the time. And the big conclusion of the paper is that historical shocks can have economic impacts even today. So like there's this persistence, and enslavement of people can persist in these ways. So this was a pretty big paper for me when I read it, and so I like to highlight it when we talk about geographic data. You should all have access to this paper. You can just put this name and year into Google Scholar, and you should have access. It's an amazing paper. It's pretty technical in some ways, but take a look if you're interested in those things. Powerful paper. Another one is with voter registration. This is actually something I've worked with, and I want to show you a few things from my dissertation work relating to voter registration records. So the question I tried to answer was, does the party of your neighbors impact your decision to vote? So we know like there's social networks, and the people in your life have pretty big influences on your behavior. And so we wondered if there were impacts of the party of your neighbors on your decision to vote. And so what I did is actually geocoded individuals in individual registered voters in North Carolina. So this is right around Charlotte. And each one of these points is a different voter, and you can see that they're registered to different houses. So you can see each one of the houses. And if you zoom out, you can see the distribution of voters, and then colored by their party affiliation. And then what I did is actually measure distances between voters to get a sense of geography. So how close are voters to each other? Closer people should have larger impacts on each other. So we used just a circle around each person to measure the composition of your neighborhood. And then so this is useful, but for our question at hand, the main question we're trying to get after is, are fewer restaurants further from downtown Pittsburgh? So that was my little aside, just two different examples of modern economic research using geographic data. These are just two examples, one that's been impactful for me, and then one that's my own research. So the question at hand is, are fewer restaurants further from downtown Pittsburgh? Using this data set, someone maybe give me an intuitive answer. What does it look like just with the picture? Zip codes further away from downtown have more or less restaurants. Drew? Okay. And why does it look like less? Okay, so like maybe down here, out past Wilkinsburg, fewer dots, maybe out here too. Yeah, and then even in these areas, there may be fewer in total. Yeah, so looking at the map, you might be able to infer something, but we want to sort of match our intuition. We want a more systematic way of performing this, asking this question. So if you're thinking through how to answer this question, what steps might we take? I've listed out some steps, but you could maybe offer some alternative ones. You're thinking through how to answer this question. What might we do? So I would maybe first try to count the number of restaurants in each zip code. That would maybe be a place to start. And then once I've done that, I've counted all of the restaurant points in each one of the zip codes. I would then maybe try to measure distances between downtown and each one of the zip codes. And that's going to be a little more complicated, but I'll give you a tool that we typically use for those kinds of things. So then we're going to measure distances between our zip codes. All right. So to break this into two parts, the first one, we're going to talk about how many restaurants are there in each one of Pittsburgh's zip codes. And this is what it looks like, actually. These are the number of restaurants by zip code, and then we have each one of the zip codes, and then we sorted them by their number of number of restaurants. If you don't know, this is downtown Pittsburgh. And then, what's Oakland's zip code? Is it the second one? Yeah, which makes sense. And then this might be Lawrenceville. So what we're going to do is actually construct this histogram in Google Colab. So there's a bunch of complicated steps here. If you were to ask Gemini how to do this, it would know. I've written out the code just to talk through and verify that the code works. The first thing is we're going to create a restaurant's geodata frame. You don't strictly need to do this, but it just sort of makes the data kind of work a little bit better. And then what we're going to do is actually take these two data sets, this zip code data, and then what we call join it with the restaurant's geodata frame. So what this does is it sort of merges those data sets together. And then all we're going to do is count the restaurants by zip code. So we're just going to go through and count these things up. I will tell you, when I was writing this example, I had an AI write these steps for me. This is not something I mean, you can get into the details of how you write these things, but, and you have to verify that it works. But when you're writing new code, personally, I would not recommend you start from scratch. I recommend you start by asking Gemini how to do it. It's how I write code these days. If you're worried that you're like breaking some rule of the universe by using AI, you are not. It's a tool we have at hand today that we didn't have in our hands 3 years ago, and you will always have it. It will never not be with you. So use it. I use it today. You can try to learn Python from scratch, all the different things. There's an infinite number of things you could learn. For most of us today, it's not worth it. So what this does is basically just counts up all the zip codes, or counts up the number of zip code counts per zip code, and then creates for us this data set. So let's just take a look and make sure we have what we want. We have restaurant count, and then we have the geometry for the zip code. Okay, so that's exactly what we want. And then all we're going to do is create a figure. So this is just a horizontal bar chart. We're plotting the zip code and then counting up the number of restaurants on the horizontal axis. And that looks like this. Okay, any questions here? So I apologize for all of the sort of geographic arguments, like we walked through a bunch of steps. We're going to do one more. If you don't love geographic information, don't take GIS, but there's an entire class devoted to these kinds of things. Lots of powerful tools. So we have a histogram here, a horizontal bar chart, telling us how many restaurants are in each one of these zip codes. The second sub-question we might be after is how far are each one of these zip codes away from downtown? Remember, we want to understand the relationship between distance from downtown and total number of restaurants in each zip code. Frankly, I'm not sure anyone's ever asked this question before. So here's the downtown zip code, which sort of stretches into the Strip District too. So what we want to do is actually, so think about a zip code. If we're trying to measure distances between zip codes, we could look at it's like, where do we place the start and the end of our ruler? So we could, try to find the closest 2 points between two zip codes, or we could look at the center point of each one of the zip codes. We need a point somewhere on the map to measure between. So the typical way we measure distances between areas is we use a centroid, which is like the center point, the center of mass of the area. So that's what I'm going to do. First, I'm going to construct all of the centroids for each one of these zip codes, and then I'm going to measure distances between them. So I have all of the centroids, and then I also have the distances in miles from downtown. And then on the vertical, on the color gradient, the more blue it is, the further away it is from downtown. So we can just verify that our measurement is generally working as it should, just visually. So as you sort of radiate out, the distances grow, which is exactly what we are looking for. And I've provided the code here. No need to get too into the weeds on this stuff. I know some of you are going to work with this kind of data on the final project, so I'm including the code here just to show you how it works. The details of these exact processes are, it's too much for this class. Their entire class is devoted to this stuff, but I just want to show you the details. And if you're interested, you can do just tons of these kinds of things. So what we're doing here is constructing a centroid for each one of the zip codes and calling it centroid. So this is, we're creating a new variable name in our data set. And then this just measures the Latin longitude for each one of the centroids. It just turns it into a Latin lon. And then we're just going to plot the centroids here. So I plotted them out. We have the downtown zip code and then each one of the centroids on the map. But we also want the distances. So I'm going to find the downtown zip code and then calculate the distances between them. Like I said before, I didn't write this from scratch. I used the 4.0 model from OpenAI to write this. And I recommend you do the same thing. So this just constructs distances using a lambda function, which is a little bit complicated, but it's the best approach here. And then we can plot out the distances using a color gradient. Okay, so it's a lot. You don't have to follow all these steps. Basically, I just found distances between centroids. So one thing we like to do when we talk about anything we've measured is find the distribution. So I'm just going to construct a histogram of all of the distances from downtown. So we have a lot of, it's a circular sort of, it's kind of round Pittsburgh. So we'd expect most of the zip codes to be sort of in this area. And then there are a few in the outskirts. Okay, so this is all of the distances on the horizontal axis and the counts. And then we also have, from before, we have all of the restaurants by zip code. So now we have two variables. They're both numerical. One of them is discrete numerical and one of them is continuous numerical. But we have two numerical variables. And the standard thing to do here is just to plot a scatter plot, which looks like this. So someone interpret what this figure is telling us. We have the horizontal axis representing how far away you are from downtown. This zip code at 0 distance from downtown is downtown. And then we have, on the vertical axis, we have some measure of restaurants. This is the main figure for our example. What is it telling us? Yeah, Jared.
Traditionally, if you're closer to downtown, the density of restaurants tends to be higher.
So the density of restaurants looks maybe slightly higher when you're closer downtown. Yeah, what else? Any sort of like nuances to that main story? Well, one of the problems with this, which we didn't account for, was that zip codes can be of different sizes, right? So different areas. And so maybe what we could do is create a normalized variable by counting restaurants per square mile or something like that, which might give us a better measure of density. Another thing to notice is like we can't really include downtown as one of our data points because we're measuring distance from downtown. I mean, maybe we could. It just depends sort of on the question at hand. But if you exclude this, it doesn't look so steep. We certainly don't have a lot of restaurants far from downtown, but it doesn't look like, yeah, there's maybe a slight negative slope, but this definitely would pull the slope up or make it more steep, more negative, more steeply negative. Okay, so this is, some of the standard practices for working with geographic data. There's an infinite number of things you can do here. And some of you are going to work with geographic data. If you have questions about data operations with geographic data that we didn't cover, I love talking about this stuff. I've spent just a ton of time working with geographic data, so I love that. And I've included a lot of code here to be able to write these things, but there's always going to be more. So if you've more interest in this after the semester is over, you can take a GIS class, give you lots of powerful tools. Okay, so I think we'll end it here. Next class, we're going to have our mini exam, which is going to cover this content and time series and relationships between variables. So it's basically like covering all of part 2. And then on Tuesday next week, we're going to start part 3. So we're going to start working with statistical models.
Did we just have one less mini exam in total for all of them?
Yeah, we're sort of going to treat the next one as like 1.5. But yeah, essentially half of a mini exam less. All right, nice seeing you all. See you next time.